My name is Andy Gickling. I'm an electronics engineer out of St. Paul, Minnesota. I work for an industrial laser systems company called Lasix Industries. I've had a unique set of experience coming from that company. Thank them very much. And what I've come to make Faire for is this robot that I built. It's called the B-Bot. It serves beers at the pool, and I'm going to tell you about it. It integrates a BeagleBone Black with a FPGA cape. So I want to start. It's unbelievable what sort of maker times we live in. Obviously, everybody's here. It's a great thing. The open source movement's going on. It's pretty dramatic. Everything I learned pretty much was online. I studied electronics in school and picked up software after the fact. So I encourage you guys to not hesitate. Just grab this stuff. The hardware's cheap. And there isn't enough makers around. I'm glad you all made it. So B-Bot is an open source drink serving robot. Free as in free beer. I put all the source code on GitHub. We'll get to that a little bit later. But it features a BeagleBone Black mini Linux computer, which I think there's a number of presentations today that actually talk about that. And I think they have a whole wing dedicated to Raspberry Pi and stuff like that. But it's a mini Linux computer with an FPGA cape. And when you combine those two things together, there's some really, really cool possibilities that normally would not be available if you're just using a microcontroller. I made B-Bot because one day my friend at the pool was, kind of laying there in the sun, and we ran out of beer. And then he's like, "Why can't you just send a robot upstairs to get us more beer?" And sure, I was like, "Okay, well, let's do it." So that was about 6 months ago. Yeah, and I love Linux, and I had owned a BeagleBone Black at the time, and I needed to just invent some project to work on Linux because it's such a fun platform. So I started thinking about what a robot needs. It needs a lot of I/O, needs computation power. Drives and servos are a must, and ideally low power consumption. So I can't just get a full Windows, Intel Core i7 computer on this robot. It's just not realistic. Unless you're NASA. You go check out the NASA robot that does have that. Okay, before you guys kill me for this slide, I love Arduino, but there are some limitations. I learned a lot of things on Arduino, actually. You can do like 80% of all do-it-yourself projects, I feel like, could be accomplished with an Arduino. But for robotics applications and some things that we're going to talk about, there's some limitations. There's typically no operating system. I mean, they have them, but it's just not as, there's not a lot of drivers. It's not as robust as what we're about to talk about. Memory is kind of small, some limited I/O, things like that. You really need an operating system to develop a robotics platform because things need to multitask. So I have multiple threads that get spawned on my BeagleBone Black application. One handles the motion control, another handles the voice control, another handles there's actually a real-time clock and GPS and things like that. So I found this awesome picture on the internet, and I was like, got to put this on there. Because that's what an operating system does. It provides drivers and lets you integrate things together much more simply than just writing straight C top to bottom. And obviously Linux, you might have heard of. It's everywhere, and there's so many resources online that you can just get for free if you just go online and search for embedded Linux, specifically surrounding the Raspberry Pi and the BeagleBone Black platform. It's developed by Linus Torvalds, as you know, and you probably wouldn't know this, but most server farms, heavily Linux. Embedded electronics, like your cell phone, Android cell phones, are all Linux operating systems. And desktop computers like Ubuntu also run Linux. BeagleBone Black, I think there was actually somebody just talking about it. I'm not going to spend too much time on this, but it's $45. Buy one for your kids and just let them have at it. It's brilliant. I mean, I thought for sure I burnt it out like 4 or 5 times. It's just bomb-proof, too. I'm so impressed with this platform. It's a gigahertz processor. It's a whole computer. And you can see my robot over there. It's got video. It talks. It does all these things. USB even. And it all comes out of the box when you have Linux. Essentially, there's just this whole body of drivers. Sometimes it's a little prickly. Sometimes it's very hard to learn initially. But the more you spend on it, I mean, you'll be really surprised at what is possible. My company actually uses embedded Linux called Yocto as an industrial platform for this very, very high-speed laser controller that we made, all free software. So we're not paying anybody royalties on the software because we didn't modify the kernel, and it's all pretty good stuff. Okay, so dramatic change here. The presentation is about what you can do when you integrate FPGAs with these embedded Linux platforms. And a Linux computer is only so good at so many things. It's good at high-level computation, but an FPGA in reality is what people use to interface with hardware. It talks to the low-level components, and it actually has the protocol interfacing on it. It's a reprogrammable circuit. It's unlike anything you might have seen. It's not sequential logic. You can arbitrarily route I/O in and out of any pin on an FPGA from software. So rather than having your breadboard, we'll get to that on the next slide. Rather than having your breadboard be all these components, you just write the software. You don't like it, you redo it. Now all the pins are different and the I/Os are different. You might have SPI on this set of pins, and then you just change it over here. So it's a very, very powerful platform. They're pretty new technology as well. This is kind of a block diagram that you can't read, I'm sure. That is essentially showing you that you have all these blocks, and you can just take them in and out arbitrarily, reprogram your device, and it's pretty cool. It's trying to get around that. Sure, if you've ever breadboarded before, this is what ends up happening. And then you're like, oh, why do my clock signals look junky over here? And just things happen. FPGAs work completely around those problems. You're able to just program your circuitry onto one chip, achieve very high clock rates and things like that. So most companies use, for example, embedded Linux or a computation platform to run an application, and then they let the application shovel data down to the registers of an FPGA, and then the FPGA shovels the data out the door. So on a robot, you have all these integrated hardware components. They might use UART or SPI or even more sophisticated protocols like PCI Express and things like that. FPGAs are capable of doing all those things, but many of the things a microcontroller or a mini computer can't do. So I'm going to talk about a couple of applications where that's specifically useful. Here is a picture of the block diagram of the BeagleBone robot. There's a .NET GUI, sends data via Zigbee, and then the data hits the FPGA, and the FPGA shovels that over to the mini Linux computer, BeagleBone Black, and then the BeagleBone Black has a high-speed SPI data link, shovels the data back down to the FPGA once it's been parsed. You guys can come see this in a lot more detail, and I can tell you more about it. I don't want to run out of time, so I'll just keep going. But essentially what we'll talk about is a couple applications where FPGA is perfect for a robotics application. Design example 1, I was just talking to this undergraduate at MIT about how he hated the fact that his previous robot project used Arduino interrupt lines to count an encoder quadrature signal. An encoder quadrature signal is essentially a signal that comes down 2 wires, and each pulse represents a certain amount of rotation of something, or linear motion as well. It's kind of like a tachometer for your car, but a lot more sophisticated than that. As soon as the count stops, you know exactly what angular position you've left the wheel at, for example. Unfortunately, when you want to use like a 4,000 line count wheel running at 30 RPM, signal rates get really high, and now if you're using an Arduino with interrupts, it's just constantly trying to count the wheels. It's not processing your data anymore. So Arduinos and things are not ideal for such an application. FPGAs can be programmed to just count the clock rate, and then as soon as the software needs to know about what the count is, they want to, hey, how fast is the wheel going? They can ask for it. It's a much more efficient design approach. Another common thing, the proliferous PID controller. Many of you maybe have used a microcontroller to PID control something. It's an engineering 101 thing that everybody learns about. Well, opencores.com has a PID controller block that you can just download, stick in, and put your variables in, and then it will control your variable for you. And that's in the fabric of the FPGA, so you don't waste any compute cycles calculating that control loop. The FPGA takes care of it for you. Another great example is hobby servo motion. Is typically a pulse train that looks like this slide here. I hope it's full screen. Oh, it's not, darn. 1.5 millisecond on time defines 0 degrees on most hobby servos, and then 1 millisecond on time is the limit of throw one direction, and 2 milliseconds is the limit of throw the other direction, and then those pulses go at 20 milliseconds. It's a very common thing. You can use an Arduino, for example, to use a PWM channel to do that, but again, it's not terribly efficient. Sometimes you have resolution problems. It's typically only a 256-bit register that defines the pulse time, for example, and you have to use up one of the timers on the microcontroller. On an FPGA, none of these are problems. You make a block that is a pulse generator, you set how long it's supposed to be on and off for, and it just blasts for you. And the best part is, say you need 20 of them. Well, FPGA, you just put 20 on them, and if you have 20 pins available, they are all available to be your pulse generation. It's very, very good for FPGA, I'm sorry, for servo motion control. I have a bunch of that on the robot as well, so if you want to see it in action, come talk to me. Another big problem that everybody faces when they use an FPGA is a lot of people get miffed by how you, I know I was, map data from user space down into the FPGA register land. And essentially, that's a very common problem. I was very miffed initially too, but there's a million ways to solve that problem. A very simple one is an SPI data block transfer. You specify a number of bits, you tell yourself what each section of bits means, and then you spawn a thread in user space that just transfers it via SPI from Linux straight down to your targeted registers, and then those go out the door, and those set all the variables and things on your FPGA. Can't go into too much detail on SPI, unfortunately, but it's a very, very effective. On my robot, it's like a 6 megahertz SPI link, so you can really push data down very effectively. So some other more abstract integration possibilities to wrap it up here are a really common thing is the Internet of Things, smart devices. They all benefit from Ethernet-based internet-ready computers, but then to interface that with hardware, you can effectively use FPGAs to take it to the next level. There's actually a gentleman that's helping on the Valent FX project over here. He's making an open hardware vision, or instead of OpenCV by Intel, there's OpenHV by Jonathan Fiat. He's a professor in France, and it's really sweet. It has all these algorithms in FPGA land that allows you to do computer vision on FPGA fabric, and they can get information from that as well. Also, high-speed data interfaces are very hard to integrate with microcontrollers. FPGAs allow that too. SATA, PCIe, GPMC is general purpose memory controller. Those are very, very fast. And BeagleBone Black has one as well, so you can use those links as well. So where's the technology going? I would encourage you guys to look into the technology, mostly because everything is going the SoC route, system on a chip. You put all of the hardware your application needs on a chip. And Altera and Xilinx have a new family of ICs that just came out that have ARM Cortex processors and FPGA fabric on the same die. This is a picture of a development kit you can buy from from Arrow Electronics. I took a seminar on it. It's remarkable. You make the Linux operating system run on the cores, and then the peripherals that you put into the FPGA around it can be mapped into the Linux device tree very, very easily. They have instructions for how to do the whole thing. So kind of like in your cell phone, everything is a SoC. All the devices are on one chip. An easy way to get started is read this book, Pong P. Chu. It's Spartan Xilinx 3 FPGA prototyping by Verilog examples. That's how I learned. It's a very, very, very well-written book. Also, you can check out my source code to do everything that I just described in this video for my beer-serving robot. All you got to do is go to GitHub and search Bbot FPGA, and you'll find me. And also look into a Raspberry Pi. Look into BeagleBone Black. Again, these computation platforms are like $45. It's amazing how easily you can get a light bulb to blink and show other people what you've achieved, because it's just all over the internet. In fact, YouTube is a awesome place to check out videos on how to do stuff. I learned a lot of stuff about the BeagleBone Black from a gentleman named Derek Malloy out of the University of somewhere in Ireland on YouTube. Also, we're trying to get this Mark I FPGA cape that goes on an Arduino, a Raspberry Pi, and a BeagleBone Black. We're trying to do a Kickstarter or something, so if you're interested in that, come get on the emailing list. And if I have time, in conclusion, it's really, really cool hardware. It's really cool software, and it's the whole top to bottom environment where industry is already there, but I don't feel like the DIY community has really embraced it because there's kind of a learning curve. I wrote all this software and I did all this stuff so that people could learn it very easily. Just go download my software. There's not a ton of documentation yet, but there's going to be. And everything's online, guys. It's all Google. Just go to Google. You'll find anything you want about anything I just talked about. Thanks for your time.